When you browse the web, it feels like a private tube between you and a website. But the internet is actually a public room. Your data hops through dozens of routers to reach its destination. If you use standard HTTP, your data is sent in plain text. Anyone managing those routers in the middle can just read your passwords. We need a way to send secrets in plain sight. Pause here and predict. How do you securely agree on a secret code if someone is listening to your very first word? A common misconception is that you just need a really good password. But if you have to send the password to the server to start the chat, the eavesdropper gets it immediately. The brilliant solution is asymmetric encryption. Here is how it works. Instead of a shared password, the server generates two things: an open padlock and a key. The server keeps the key safe and sends the open padlock across the dangerous internet to you. You take your secret, put it in a box, and snap the server's padlock shut. Here's the magic part. Once it clicks shut, even you cannot open it back up. Only the server's private key can unlock it. So you send the lockbox back, the eavesdropper sees it, but without the private key, it is just useless metal. The server receives it, unlocks it, and safely read your secret. But there is a catch. This padlock math is incredibly heavy and slow. If we used it for every single image and text on a web page, the internet would crawl. So we do not use the padlock for the whole conversation. Instead, you use the heavy padlock just once to send a simple, lightweight shared key. Notice what happens next. Once the server receives this shared key, the heavy padlock is thrown away, and you both talk through a fast, secure tunnel. This is the famous TLS handshake. But wait, we have a fatal flaw. What if the eavesdropper intercepted the connection early on and sent you her own padlock? You would lock your secret with her padlock, and she could read everything. We need proof of identity. This is why the server does not just send a padlock, it sends a certificate. Think of this as a digital passport stamped by a trusted authority. Your browser comes pre-loaded with a list of these trusted authorities. If the stamp matches, you know the padlock really belongs to your bank and not an imposter. Watch how this all comes together. The trusted certificate, the public padlock, and the fast shared key combine to create that familiar green lock in your browser. So HTTPS is not just a hidden code, it is a three-step dance. You verify the server's identity, you safely trade a fast secret key using a public padlock, and then you talk securely. Next time you see that little lock icon, you will know exactly the cryptographic gymnastics happening behind it.